So today I'm just going to continue studying. Basically do the same thing that I did on the last streams. Just gonna review a data structure and then I'm gonna do some quizzes. So this is the one for today. I think the main difference is gonna be on the push and pop, obviously, from the last one, which was a ring buffer. I think the stack is probably a lot simpler. Yeah, so it's basically the same thing, but it just decreases the, which was already something that I learned on the previous time on the ring buffer. So on the ring buffer, it was increasing the length on both. I think it was increasing the length, but it was using different pointers. Oh, here it decreases the length. So it was increasing the pointers. Yeah. Then I asked ChatGPT why not decrease the pointer here, and the answer was because if you did that, then it would be a stack. So if you had 2 pointers and decrease one, you get the same behavior as a stack, because then it's as if you are removing the thing on the top instead of just rotating. That makes sense. And here there isn't 2 pointers, so I think it's just one. It's basically very similar to the vector example as well. Basically the same thing. And the only difference is that on the pop, it just decreases. So I'm pretty sure I'm gonna ask GPT what it thinks. Yeah, ask Grok this time. From what I see, I think it's fine. It's basically very similar to the other ones. It gets this as a pointer. This is a no null. Maybe you should look into this again on the documentation. But I assume it's basically the same behavior as a raw pointer. Then it creates the layout structure based on the capacity, uses alloc to allocate the memory when you're initializing with capacity. And here is just getting that as a pointer, then adding the length to go to the last position on the vector, then adding the elements and using the pointer dot write to actually write the memory on that place. So pretty simple, and here is basically the same thing. When you read on Rust, it's because of the ownership model. When you read, it's gonna delete the memory. So this is kind of like deleting the memory because you're reading from the place. I think that's what's happening. I'm pretty sure that it is correct. There's a couple of extra methods. The growth is basically the same. So here, I assume that Grok is gonna tell me that choose the checked multiply here instead. And which is basically the same thing that's happened on the other examples. I don't remember really well if I can self-cap. checked, but yeah. And then you do the, I forgot that I don't have the Vim findings here. You can either do unwrapped or unwrap or you can do this expect, which is basically checking the throw. Overflow, whatever, doesn't matter the message. But I've heard somewhere that this is not very good to do. You should always prefer to use the question mark when you can. And I think the question mark forces you to change the type of the function in some cases, because the question mark is gonna make you return a result type. And the result is a type on Rust that allows you to wrap the original type into something that allows you to either return an OK type or an error type. It's basically something that allows you to tell the program whether or not the result was okay or you got an error. Yeah, but in this case, it seems that it's kind of hard to know. I'm not gonna. I should open the other temporary project to compile this and check to see if it's an error or not. But I don't feel like doing this now. I'm just gonna do quizzes today because it seems very simple, this example. This drop is different than the vector one, I think. Maybe this one could be improved. There's looping over the length, and then using this pointer API to drop the memory and adding iterating over the elements basically. I think one thing that was a common thing on the other ones as well is to decrease the length, I think, as you loop and drop the elements, because if you are dropping and then the program panics, you can have a memory leak. I think that's the issue. So you should always decrease the length inside of the loop, I think. And then here, size of, I think that the name of this is zero size type on Rust when you only have the color thing. And I think this is a common thing on Rust, where the name is like the expression is zero cost abstraction that the people talk about, but I don't know very well like what. Maybe there's an interesting question to ask actually. What does it mean to have a zero cost abstraction from the compiler's point of view? Yeah, so I think that is basically the same pattern as the other ones. First, you delete or you remove the memory for the elements, and then you remove the memory for the whole thing, the vector itself. It seems, well, actually, so the stack is just gonna be calling the methods. Kinda, maybe this is something that I should ask because of this inner pattern here. That first time that I was trying to convert micrograd from Python to Rust, I think GPT or some other LLM told me to use this inner thing here. And I didn't understand why, because it seems kind of redundant if you're just calling the methods of the other implementation. But I assume that there is a reason for this, probably. Yeah, but the two questions about the inner and the zero thing abstraction, zero cost abstraction.
Show how stack T is just a thin, intention revealing wrapper around vec T while still getting all the LIFO semantics right. No major adjustments are needed. What's especially good composition over inheritance/re-implementation? You reuse the vec from the previous exercise exactly as intended. This is the correct design for this kind of exercise series. ZST handling the special casing in vec new with underscore capacity and grows textbook correct and matches what std vec does internally. Most people forget this and get surprising behavior with or unit structs. Drop correctness the test underscore drop underscore runs is chef's kiss. It proves that both explicit pop and the stack zone drop directly run destructors. This is the kind of test that catches 90% of custom collection bugs. Minimal but complete API push /pop/peek underscore mut /len /is underscore empty /with underscore capacity is exactly what a pedagogical stack should expose. No bloat. Unsafe usage. All the PTR write /PTR read /drop underscore in underscore place is perfectly placed and justified. No unnecessary unsafe blocks. Tests they cover the happy path, edge cases, none on empty, mutation via peak underscore mut, capacity pre-allocation, and drop semantics. Perfect. Very minor nits, optional Polish only. These are not bugs, the code is correct as is. Consider them only if you want to make the solution even more textbook perfect. Tiny dot comment consistency, the vec has nice section comments. The stack could get a one-liner at the top for symmetry. Rust LIFO stack built on top of our minimal custom vec.pub struct stack t inner, vec t, new type pattern, purely stylistic. Some people prefer the tuple struct form for such thin wrappers. Rust pub struct stack t vec t, then the methods become self.0.push. etc. Either style is fine. Your current name field version is actually more readable for learners. Capacity growth comment in vec grow, you could add a one-line comment explaining the doubling strategy. Many students wonder why *2 Rust can grow itself if stdmem size underscore of t0 return amortized 01. Push via duck doubling same policy American Samoa std vec let new underscore cap if self duck cap 01 else self. Cap 2. Overflow safety. Pedantic. Usize max for ZSTs plus len plus equals 1 can theoretically overflow in release mode. You could guard the increment, but it's completely unnecessary for an exercise. You'd never hit usize max elements. Leave it. Would I change anything for the official solution? No. If I were grading this as the exercise solution, I'd give it full marks and probably use it as the reference implementation. The code is already better than most minimal stack examples you see online because it properly handles ZSTs, allocation errors, and drop semantics. Quick suggestion for the exercise prompt itself: if you want to make the exercise slightly harder / more educational in the future, you could add one of these requirements to the stack part. Implement stack without exposing the inner vec, i.e. keep the field private. Dot. Add a clear method that drops all elements but keeps the allocation. Make stack implement into iterator, consuming, and iterator, by reference. Dot. But as it stands right now, your solution is ready to ship. Great work. This is exactly the level of care I like to see in these reconstruction exercises. If you want me to review the next one, Q, maybe, or generate a student version with some parts intentionally left blank, just say the word.
Yeah, I noticed that Grok is not very good for these types of things. GPT seems to be better, and Gemini seems to be better as well. But Grok tends to be better for things that require like, new information. I guess obviously because you can use Twitter to pick it up. This time I'm gonna use ChatGPT again, just see if it says anything different about the implementation. Because I assume that it's gonna tell me about the checked mu that I talked about before. And maybe some other stuff about the drop there, about the panic and the drop. Basically just sending the same prompt. Just see what it says.
Overall verdict: this is an excellent production quality solution for the exercise. It's clean, correct, safe, within the constraints of a custom allocator, pedagogically spot on, and the tests are comprehensive. You clearly understood the point of the exercise. Show how stack T is just a thin, intention revealing wrapper around vec T while still getting all the LIFO semantics right. No major adjustments are needed. What's especially good composition over inheritance / reimplementation, you reuse the vec from the previous exercise exactly as intended. This is the correct design for this kind of exercise series. ZST handling the special casing in vec new with underscore capacity and grow is textbook correct and matches what std vec does internally. Most people forget this and get surprising behavior with or unit structs. Drop correctness, the test underscore drop underscore runs is chef's kiss. It proves that both explicit pop and the stack zone drop correctly run destructors. This is the kind of test that catches 90% of custom collection bugs. Minimal but complete. ZSTs, zero size types, plus zero cost abstractions in Rust. These two ideas are at the heart of why Rust feels so magical for systems programming. Let's break them down exactly as they relate to the vec / stack code you showed. 1. What is a ZST? A zero size type is any type where stdmem size underscore of t equals 0. Common examples: Rust struct unit ZST struct phantom tstd marker phantom data t also ZST never ZST uninhabited type empty tuple. The classic ZST even though size underscore of unit equals 0. The type system still treats it as a full-fledged type. You can put it in a vec unit, store it in a struct, pass it by value, etc. Why does Rust need special handling for ZSTs in collections? Look at your vec new and grow. Rust cap if stdmem size underscore of t0 usize max l0. This is not a hack. It's the correct and idiomatic thing to do. Exactly what std vec does internally. For normal t, capacity equals 0 means no allocation yet. For a ZST, every element takes 0 bytes, so you could theoretically store infinite elements without ever allocating. Setting cap equals usize max tells the code we can never run out of capacity, so push never calls grow, and you never allocate. Len still tracks how many logical elements exist, important for drop, pop, etc. From the compiler's standpoint, the compiler knows the exact size and alignment of every type at compile time. Monomorphization. When t, ZST, the layout of vec t is optimized away to essentially just len, usize. The pointer becomes a dangling non-null that is never dear for for data. All the pointer arithmetic, as underscore ptr. Add, I, still type checks, but the generated machine code for a ZST vec is tiny, often just a counter increment. This is why you can write vec, or vec phantom data something and it behaves perfectly with 0 runtime cost. 2 zero cost abstractions. What does zero cost actually mean? Rust's slogan is, you don't pay for what you don't use. And you only pay for what you do use. Zero cost means the abstraction disappears at runtime, or becomes as cheap as writing a low-level code yourself. In your stack T example, rust pub struct stack T inner, vec T, leftward arrow just a new type wrapper. Every method is a one-line delegation. Rust pub fn push mut self, item, T self dot inner dot push item. How is this zero cost? The Rust compiler does several things. Monomorphization stack I32 and stack string become completely separate types with their own specialized code. Inlining the compiler almost always inlines these tiny delegation methods. After inlining, the generated assembly for s.push 42 is identical to v.push 42, where v was a plain vec I32. Layout optimization slash new type optimization because stack T contains only a single vec T field and has no extra data. The compiler can and does layout stack T exactly like vec T in memory. There is no extra pointer in direction or padding. LLVM optimizations, dead code elimination, constant propagation, etc. remove any trace of the wrapper. So at runtime, using stack is not slower than using vec directly. It is the same code. This is the zero cost abstraction in action. You get a new semantic type. Stack equals LIFO only with a restricted, safer API, but you pay nothing in performance. Do other languages have this? Language has true zero cost abstractions. Why not Rust? Yes. Very strong. Ownership plus borrow checker plus monomorphization plus aggressive inlining plus layout control C++ mostly. Templates plus inline. Good. But you can accidentally pay cost. Virtual functions, exceptions, etc. Zig yes. Similar philosophy. Compile time code execution plus no hidden control flow no interfaces are fat pointers with runtime dispatch Java slash C# no heap allocation plus virtual method tables plus GC Python slash JS no dynamic typing plus interpreter overhead. Rust and Zig are the only mainstream languages where you can add layers of abstraction and be confident the compiler will erase them completely. Why does Rust love the inner vec T delegation pattern? This is called the new type pattern, or sometimes wrapper slash facade. Reasons Rust uses it everywhere. Semantic typing stack T and vec T are different types. The type checker prevents you from calling stack.insert 0 x or stack.sort, things that would break the LIFO contract. Encapsulation slash API control, you only expose the operations that make sense for a stack. Future changes to the internal representation, e.g. switching to a vector or a linked list, won't break user code. Zero cost is explained above. The compiler erases the wrapper. Drop, debug, etc. are automatically correct because vec already implements them properly. Stack gets them for free via hashtag derive or delegation. Composition over inheritance. Rust has no inheritance, so this is the idiomatic way to build higher level types. When should you use the inner wrapper? Use it when you want a restricted or specialized interface, stack, queue, set, etc. You want to enforce invariance that vec alone doesn't guarantee. You're building a public API and want to hide implementation details. You want a named, intention revealing type. Stack reads better than vec in some contexts. Don't use it when you just need a vec and don't care about the extra type. Performance is so critical that even the theoretical extra inlining step bothers you. Extremely rare. The compiler is usually perfect here. In your exercise series, this pattern is exactly the point. Teach people that stack is not a re-implementation, it's a view on top of vec. The student learns composition, encapsulation, and zero cost abstractions all at once. So yes, your stack code is not redundant. It is the correct and idiomatic way to do it in Rust. The compiler sees it as just a nicer name for a restricted vec and optimizes accordingly. Let me know if you want a quick demo of the generated assembly. I can show you how identical the two versions become, or how to add hashtag repair transparent to make the new type guarantee identical layout. This is a strong exercise solution overall, especially for the goal you described, reconstructing partial implementations. It demonstrates understanding of manual allocation with stdalloc ownership plus drop to write slash ptr read composition, stack T over custom vec T, basic API ergonomics tests for behavior plus destruction for a learning project. This is already above average. The stack T itself is clean and appropriately thin over the vector. Most comments below are about the custom vec T, since that's where correctness and subtle Rust reasoning live. High level verdict, what's good one? Stack abstraction is exactly right. Stack T delegates to vec T, push pop, popeek, last peak underscore mut, last underscore mut. That's the right design. 2. Good API coverage you included. No with underscore capacity push pop peak underscore muddleness underscore empty. That's enough for a real stack exercise. 3 tests are meaningful, especially Rust test underscore drop underscore runs. That's an excellent inclusion because it checks ownership slash destructor behavior, not just values. What needs attention? 1. ZST handling, size underscore of T0 is incomplete. You partially support zero size types with Rust cap size max ptr dangling. That's correct in spirit. But push currently does. Rust ptr write self ptr as underscore ptr add self len. Elm for ZSTs. Pointer arithmetic on dangling pointers is weird territory. Standard library handles this specially. Better approach. Inside push. Rust if size underscore of T0 self len 1 stdmem forget elm return and in pop. Rust if size underscore of T0 if self len 0 return none self len 1 return some unsafe stdmem 0. Though 0 for all ZSTs is safe because no bytes exist. If this is just educational, you can also simply state ZST support is partial and skip it. That may actually be cleaner pedagogically. 2 potential overflow in growth logic. Rust let new underscore cap if self cap 0 1 else self cap 2 if cap is huge. Multiplication can overflow before layout array catches it. Better. Rust let new underscore cap self cap check underscore mul 2 expect capacity overflow 3. Panic safety and drop. This is acceptable. Rust 4 and 0 self len drop underscore in underscore place. But if one element's destructor panics, remaining elements leak. That matches many manual implementations, but ideal pattern is Rust while it's some underscore self pop because length decreases before drop. Then partially drop state remains consistent. 4. Missing cap accessor, optional, since you expose with underscore capacity, useful for tests. Rust pub capacity self, use size nice educational edition. 5 main is unnecessary in exercise file, not wrong, but if this is a library style exercise, I'd move examples into tests or docs. Subtle correctness check your pop is good. Rust self.len, 1 ptr read. Length decreases before moving out. Excellent. That matters if T panics later during drop elsewhere. Stack layer feedback, the stack wrapper is good, but I'd consider add default Rust impl T default for stack T from default. Self new add clear Rust pub clear mud self while self pop is underscore some add into underscore inner. Advanced, could expose own vector. Test improvements add LIFO stress test Rust 4 and 0. 1000 push I 4 and 0 1000 rev assert underscore EQ. Pop, some I add grow test push beyond initial capacity. Add ZST test Rust struct marker limit stack new s push marker assert underscore EQ. S. Len. 2 if this is for learning reconstruction exercises, this solution is actually excellent because it contains enough moving parts, real unsafe blocks, delegation patterns, edge case logic tests revealing intended behavior that makes it ideal for fill in the missing implementation style drills. My suggested minimal adjusted version if you only fix 3 things. Do these. Check growth overflow explicit ZST note or full ZST handling drop via repeated pop final score for an educational custom data structure project. 8.8/10 for production code. 4/10 because writing custom alloc back vec safely is extremely hard and STD already exists. For teaching ownership slash unsafe Rust. 9. 5/10 my honest recommendation, keep this solution mostly as is but do not over polish it into STD vec. The point of exercises like this is understanding raw pointers allocation lifecycle move semantics destructor behavior abstraction layering and this code succeeds at that. One important pedagogical suggestion since users reconstruct from partial solutions, add comments like Rust safety, len cap guaranteed after grow ptr points to allocated memory for cap elements that helps learners understand why unsafe is valid. Final verdict yes, keep it. Only make adjustments if you want stronger correctness around ZSTs plus overflow. Otherwise it's already a very solid stack exercise solution.
I'm curious about what ChatGPT is gonna say about the same question there. But I'm glad I remembered the checked mu thing here. And this was slightly different, but basically the same thing. I'm not gonna change this, I'm just gonna leave it like that. And I'm gonna do quizzes after.
These are excellent Rust questions because they touch the real philosophy of the language. What zero-cost abstraction actually means? Show zero-sized types, ZSTs, work why wrapper structs like stack inner, vect are common. How the compiler sees all this. These ideas are deeply connected. Part 1. Zero-cost abstractions in Rust. Meaning a zero-cost abstraction means you write higher level, safer, cleaner code, but after compilation it runs as fast as if you wrote low-level manual code. This phrase became famous from Jarnster Strub, C++, and Rust strongly follows it. Meaning, iterators instead of raw loops, traits instead of manual dispatch wrappers instead of naked pointers, closures instead of function pointers, enums instead of tag unions, and the compiler optimizes away the abstraction overhead. Example Rust lets i32 vec.iter.map x2.sum looks high level. Compiler may turn it into something like Rust let mutasc 0 4 and 0. Len ACC data I2 no iterator objects at runtime. No callback overhead. No GC. No virtual dispatch, usually. How? Rust uses monomorphization, generic code specialized per type, inlining LLVM optimization, static dispatch, escape analysis, dead code elimination. Part 2. Zero-sized types, ZSTs. What is a ZST? A type that occupies 0 bytes. Examples: Rust struct empty struct marker struct phantom tcheck, Rust size underscore of empty 0. Why would this exist? Because not every type stores data. Sometimes a type only represents a capability, a marker, compile time, information, ownership, relation, state, machine state, trait, implementation tag. Example: marker types Rust struct read only struct writable struct file state ft i32 underscore state phantom data state. Now Rust file read only file writable. These are different compile time types, but read only stores nothing, so no runtime cost. How compiler views ZST? Compiler knows Rust struct empty contains no fields, so size equals 0. Alignment usually 1. Multiple instances need no storage. Creating 1 means nothing to allocate. This Rust leave empty let empty may generate no memory operations at all. Weird consequence: you can have Rust vec empty with length 1 million and no heap memory for elements. Only metadata ptr len cap exists because each element is size 0. How can multiple elements exist if no memory? Because identity is logical, not spatial. The vector stores len equals 1 underscore 0 0 0 underscore 0 0 0 no bytes needed per item. Compiler slash runtime knows indexing returns an empty pointer. Weirdness with ZST. Normal pointer arithmetic. Rust ptr.add 1 means move by size underscore of t. For ZST, Rust size underscore of t 0, so pointer never moves. That's why custom vec implementations need special handling. Part 3. Why this is zero cost. Example: Rust phantom data t tracks ownership slash lifetime at compile time. Runtime size Rust 0 bytes, meaning you gain borrow checking guarantees for free. That's classic zero cost abstraction. Part 4. Do other languages have this? C++, yes. Templates plus empty base optimization. C struct empty size of empty 1 usually, but compilers optimize empty inheritance. C++ inspired much of this idea. C no direct equivalent. No generics, no type level abstractions. Mostly manual zero cost by writing low level code directly. Java mostly no. Objects have headers, references, heap allocations. Generics use type erasure. Abstractions often cost runtime overhead. Project Valhalla aims to improve this. Python no. Everything is runtime objects. Huge flexibility, little zero cost behavior. Go partial. Structs can have zero sized fields. Go struct, which is like Rust ZST, but interfaces often imply runtime dispatch. Less aggressive zero cost philosophy than Rust slash C++. Why some languages don't have it? Because they optimize for other goals. Dynamic reflection, garbage collection, runtime polymorphism, simplicity, rapid development. Rust optimizes for predictable performance, memory layout control, compile time guarantees. Part 5. Why stack inner vec t exists? Excellent observation. Rust pub struct stack t inner vec t and methods just forward calls. Looks redundant, but it often is very useful. This pattern equals new type slash wrapper slash composition instead of inheriting from vec. Rust prefers composition. Why not just use vec directly? Because vec t exposes many operations. Rust insert index, remove index, sort, reverse tree clear, but a stack should expose only. Rust push pop ek wrapper restricts the API. That preserves invariance. Example: if you expose raw vec, Rust stack.remove 0 that breaks stack semantics. Wrapper prevents misuse. Why Rust uses this pattern? Often Rust has no inheritance like Java slash C sharp. So instead of Java class stack extends vector, Rust uses Rust struct stack inner vec t. This is composition over inheritance. Zero cost. Yes. Compiler usually optimizes Rust self.inner.push x into direct call. Wrapper often disappears entirely after inlining. When should you use wrapper types? Use wrappers when you want. 1. Restrict API expose only safe slash domain specific operations. 2. Add meaning Rust meters f64 seconds f64 user ID use 64 different semantic types. 3. Enforce invariance Rust non-empty vec t sorted vec t stack tqt4. Add trait implementations, maybe display, serialize, etc. When not to use wrapper if you add no meaning, no invariance, no API shaping. Rust struct my vec i32 with no purpose equals noise. How compiler sees wrapper struct Rust struct stack t inner vec t memory layout is basically same as contain field. For one field wrapper, it's usually just the same bytes as vec t. No hidden inheritance object. No beatable. No object header. Mental model your code. Rust stacked up push 5 human sees. Stack abstraction compiler often sees. Call vec push on those bytes. Why Rust loves this? Because you can model the world richly. Rust password string email string meters f64 stack t vec t without paying runtime cost. That's the magic combo. Strong types, expressive API, zero cost abstractions. Final intuition. Rust asks, can this safety slash design idea exist purely at compile time? If yes, it tries to make runtime cost vanish. That's why ZSTs, wrappers, iterators, traits, lifetimes, phantom types all exist. Practical rule for you when writing your own code. Ask, does a wrapper give semantic meaning or protect invariance? If yes, write word arrow, use it. Is it just renaming with no benefit? If yes, write word arrow, probably skip it. Final summary: ZST a type with size 0 bytes, used for marker slash state slash type info. Zero cost abstraction, high level code compiled into low level efficient code. Wrapper structs with inner used to restrict APIs, add meaning, enforce invariance. Why Rust uses it so much? Because Rust chooses composition plus compile time guarantees instead of inheritance plus runtime machinery. Honest truth: once this clicks, Rust stops looking verbose and starts looking surgically precise. Yes, this is one of Rust's strangest and most powerful concepts. At first glance, a zero-sized type, ZST, looks useless. Rust struct empty struct marker. You ask, if it stores nothing, why does it exist? That question gets to the heart of Rust. Types are not only for data storage. Types are also for meaning, compile time rules, ownership, modeling, state tracking, trait selection, API contracts. A type can matter even when it occupies 0 bytes. Core idea: a type has 2 different roles. 1. Runtime role: what bytes exist in memory. 2. Compile time role: what operations are allowed. What traits are implemented. What state is represented. What invariants exist. ZSTs have no runtime payload, but they still fully participate in the type system. That's why they matter. Example 1. The unit type Rust. This is Rust unit type. It means there is exactly one possible value, and it contains no information. Like mathematical unit. Why useful? Because functions sometimes return nothing useful. Rust log underscore message println. Hello actually returns Rust log underscore message that lets every function return a value consistently. Why better than void languages like C use void? Rust instead uses a real type. That means Rust lets log underscore message x his type. This lets it work in generics. Example: Rust result error means success equals no data needed, failure equals error info. Very common. Why is valuable? It means success slash failure without dummy values. Instead of Java result boolean error or weird sentinel values. Rust uses Rust result error cleanly. Under the hood of compiler knows Rust size underscore of 0. There is only one valid value. Rust, so storing it requires no bytes. Example 2. Empty struct Rust struct token equivalent to Rust struct token also 0 sized. Why useful? Because it is a distinct type, different from Rust struct admin struct guessed all 0 bytes, but different meanings. Type level meaning Rust integer underscore admin only admin allowed. No runtime storage needed. Example 3 marker type slash state machines very important Rust pattern. Rust struct connected struct disconnected struct socket state FT I32 marker STD marker phantom data state. Now Rust socket disconnected different compile time states. Methods Rust impl socket disconnected from connect self socket connected. Now compiler prevents Rust socket send if disconnected no runtime state flag required. That's huge. Example 4 iterators returning sometimes you care only about side effects. Rust vec.iter for underscore each x printl. X closure returns. Means no meaningful produced value. Example 5 closure slash traits a closure with no captured variables may itself be 0 sized. Rust let printl. Hi sometimes compiler stores no environment. How can something exist if size equals 0? This is subtle. Rust separates value existence. A value can exist logically. Memory storage a value may need 0 bytes. Example Rust leave led 2 logical values. No bytes necessary. Think like compiler 4. Rust lets compiler may generate nothing. No stack slot. No move. No memory writes. Just type checking info. Can references to ZST exist? Yes. Rust letter. How? Reference must point somewhere valid. Compiler may use a dangling but aligned non-null placeholder address. Because no bytes are accessed. Weirdness. Arrays of ZST Rust 1 underscore 000 underscore 0001 million unit values. Memory used for elements. 0 bytes. Only array metadata slash context matters. Vec of ZST Rust vec you can push a million times. Length increases. No element heap allocation required. This is why custom vec implementations need special handling. Why is this useful? 1 type safety without runtime cost state markers, capabilities, permissions. 2 generic uniformity need a return type. Use. Need success with no data. Result. E3. Compiler optimization no unnecessary bytes. 4 API design types encode meaning. Potential danger slash gotcha is now the real part. Danger 1 pointer arithmetic breaks expectations for normal type. Rust ptr.add 1 moves forward by size underscore of t. For ZST, Rust size underscore of t 0 so pointer doesn't move. That can break handwritten allocators slash containers. Exactly the issue in your custom vec. Danger 2 capacity logic if each element costs 0 bytes. How many fit? Infinite-ish. Rust often uses Rust use size max as conceptual capacity. Custom containers need special logic. Danger 3 assuming addresses distinguish values Rust as const addresses may be meaningless slash reused. Don't rely on identity. Danger 4 misunderstanding semantics Rust result. Error some beginners think why not bool. But bool means 2 states. 1 success state, 0 info. Much clearer semantics. Danger 5 over engineering people discover ZSTs and build type state systems for everything. Sometimes runtime bool is simpler. Use when it adds real safety. Important mental model in normal struct says, here's data. A ZST says, here's meaning. That's profound in Rust. Why instead of nothing? Because functions compose better when everything returns a type. Example, Rust FNA, FNBTX, T now generic systems stay uniform. No special void hole in language design. Comparison to other languages C void exists, but not a real value type. C++ has empty classes. C struct empty but size usually at least 1 byte is object rule. Rust cleaner here. Go struct very similar to Rust ZST. Used for sets slash channels. Java slash Python no true 0 sized user types in same way. Real Rust examples you'll see hash set T internally often like Rust hash map T because only keys matter. Value is unit. Brilliant use of ZST. Phantom data Rust phantom data T tracks ownership slash lifetimes with 0 bytes. Used heavily in unsafe code. Deep compiler perspective compiler stores. Type metadata trait implementations borrow rules variance drop behavior even if runtime bytes equal 0. So 0 sized means 0 runtime storage not meaningless final intuition ZSTs are proof that in Rust types are for more than memory layout. They encode logic. They enforce rules. They describe state. Sometimes all of that can happen with 0 bytes. One line summary a 0 sized type is a value that carries compile time meaning instead of runtime data. If you'd like, I can also explain the insanely weird relationship between ZSTs, enums, option, and how Rust can represent some slash none using 0 extra bytes. That's where ZSTs become mind bending.
I'm just gonna do some of the quizzes. I think this is an error. It's because he's using the vector here and then trying to print. That's pretty easy. This one I remember, I think it's 54 the answer. But I remember by memory. I think the reason why is obviously because of the operator here. I think this operator here consumes the first two. So this one is gonna be the rest. Yeah, because then it becomes a range object, I think. So like this thing is a range object. It's probably a range is probably a struct, which is the default type that they use to implement this type of behavior here. So these two dots here say how many ever elements or how many like essentially like infinite kind of amounts of elements, I think, after the one. But it's not infinite in the practical sense, obviously it's just lazy evaluation probably. And then what the first should do is consume this first two, I think. So these ones would be the next indexes on the list, I think. Or indices. I don't remember really well. Or maybe actually not. Maybe it's the other way around. I do remember that the x index captures the letter in the middle, which is 6. But since it's in bytes, it's gonna be ASCII code, which is 54. That's what I remembered from the explanation. But now I don't remember. I don't know for sure if y isn't 0 and x equals 1. I think that's probably more likely, to be honest. And then that would be weird. So I'm just gonna answer and the solution. So the y in this case is the two dots. So a range element. That's why it works, I think. The first operator transforms this into a range, and the other one gets the one index, which is 6. Y equals this. Does the final print as this? By string literal. Range through, get the dynamic slice, size of slice. Yeah, so I didn't remember correctly. So from what I understand there from the explanation, it seems that this one these two dots here capture 0 and 1. It must be just 0, because x is going to be 1. But then y... There's a couple of questions I have on this. I'm just gonna listen to ChatGPT, probably ask ChatGPT about it. I'm thinking about what happens if you have more elements on either side. Because if the two dots are the 0 here, and the x is the 1, then what would happen if I have more elements? Does it compile or doesn't?
Yes, this is exactly the kind of question that means you are starting to think like a systems programmer. What you're noticing is, how can a vector grow if no memory is written? That feels illegal, but it's actually valid because for CSTs there is nothing to store. The danger is not missing memory. The danger is that many low-level algorithms silently assume Rust next underscore element ptr1 which stops being meaningful when each element is 0 bytes. Let's break your implementation apart carefully. Core fact 4. Rust t then, Rust size underscore of, t0 line underscore of, t1 which element requires, no bytes, no storage slot, no offset, so 10 values of require exactly the same bytes as 0 values. That's not UB. That's valid layout math. What your vector you wrote, Rust pub note, self let cap if size underscore of, t0 u size max l0 self ptr, non-null dangling, len, 0 cap. This is actually the standard strategy conceptually. Why u size max capacity? Because capacity means how many elements could fit before reallocating. For CST, each element costs 0 bytes. So effectively, Rust infinite capacity, but since capacity is stored in usize, Rust usize max is sentinel. Why non-null dangling? Because vec t needs a pointer field, even if no allocation exists. Rust requires raw pointers to be aligned non-null in many APIs, so it uses Rust non-null dangling, which means a fake pointer value that must never be dereferring for real memory access. It is legal as placeholder. Why this is not UB yet? Because merely holding a dangling pointer is allowed. UB happens when you dereference invalid pointer read / write through it violate aliasing rules out of bounds access. Just storing it as metadata is fine. Where your code gets dangerous, here push Rust ptr write self.ptr.as underscore ptr.add self.len elem self.len 1 for CST. Rust add self.len moves by Rust self.len 0 bytes, so pointer never changes. Still same dangling address. Then Rust ptr write ptr elem. This looks like writing to invalid memory. Why is this subtle? Because for CST, ptr writes 0 bytes. No actual memory access occurs. Important distinction: this operation conceptually initializes a value, but machine code wise, Rust writes 0 bytes, so nothing happens. That's why it can be valid. But why is this still risky? Because APIs involving pointers often still require the pointer to be valid /line for the type, even if 0 bytes accessed. Rust's standard library handles this very carefully. Your custom code may rely on assumptions that are easy to get wrong. That's why custom vec t implementations special case CSTs instead of using generic path. The safer standard pattern instead of Rust ptr write. Do Rust if size underscore of t0 len 1 for get elem return, meaning consume ownership of elem, no storage needed, just increase logical length much clearer. Why forget elem? Because push takes ownership. If you don't store it, you must prevent immediate drop. For CST this often doesn't matter physically, but semantically it preserves ownership model. What about pop? For normal type, Rust read bytes from memory. For CST, no bytes exist. So standard approach, Rust len 1 return some mem0 or equivalent construction. Since every value of is identical, why changing length without data is fine because len means number of initialized logical elements, not bytes occupied. Those are different. For normal types they correlate. For CST they don't. Example Rust vec len 1 underscore 000 underscore 000 means 1 million valid unit values exist logically since unit has exactly one possible value, no bytes needed. Other weird outcomes, yes. Many. Weird outcome 1 all elements have same address conceptually. Rust vec 0 vec 1 vec 2 for CST, addresses may be identical. Because no storage separation exists. That shocks people. Weird outcome 2 iterators advance without pointer movement normal iterator. Rust ptr1 CST iterator must instead do Rust index 1 because pointer cannot encode progress. Weird outcome 3 capacity meaning changes normal. Rust capacity byte size underscore of TZST. Division by 0 impossible. Need sentinel logic. Weird outcome 4 slices of ZST Rust 100 length equals 100. Data bytes equals 0. Still valid slice. Because slice metadata is ptr len length carries meaning. Why compiler allows this? Because type semantics say a value exists. Memory layout says needs 0 bytes. Those are independent facts. Why this doesn't collapse Rust? Because compiler instilled explicitly special case CSTs in vec slice iterators raw vec internals allocation math. They know 0 size types exist. In your code, did you fully solve it? You partially solved it. Good. Rust cap usize ma returns early dangling ptr excellent instincts. Still fragile. Using generic Rust ptr write ptr read add self.len for ZST path. Better to special case push / pop directly. Why it feels wrong? Your intuition is based on objects occupy memory. Rust refines that into some objects occupy memory, some occupy only type, meaning that's the leap. Deepest mental model for ZST containers. The vector stores count, not data. That count is enough to reconstruct elements because elements contain no information. Final summary: your implementation prevents disaster mainly by no allocation needed, fake non-null aligned pointer max capacity sentinel 0 byte operations happen to be harmless, but robust implementations go further and explicitly special case CST operations. One line truth: a vec is basically not a memory buffer. It is a counter pretending to be a vector. If you'd like, I can also explain how the real STD vec t internally handles ZSTs and why vec never type and vec are opposite extremes.
Just gonna follow. Go to the next one. But since this is a reference, I think it works. Maybe not, actually, because yeah, I think this is a problem because I don't know for sure, but just based on intuition, it would make sense that Rust would prevent this, because then if you create a pointer that's not mutable and then you create another one, then you can have undefined behavior with the first one, I think. But maybe not. Maybe Yeah, because of the ownership model, that's probably the reason. So, but actually, I'm not really sure about this because it's a reference. They're both references. So X should be the thing that owns the value. I think it doesn't compile, but I'm not really sure. Like maybe it does. Let's see. I'm gonna guess that it doesn't. Yeah. But I'm not really sure if my explanation there makes sense or not. Yeah, it is basically what I was saying.
Rust mainlet x y0 1 print b 066 yx first. Does this compile? No, this does not compile because rust 0 1 on the right hand side is an expression, not a pattern. The token rust is only valid in certain syntactic places. Patterns let x y tuple ranges 0 10 struct update syntax etc. but not as a tuple. This is a fun Rust puzzle. Let's go step by step. Rust mainlet x y0 1 print b 066 yx first. Does this compile? No, this does not compile because rust 0 1 on the right hand side is an expression, not a pattern. The token rust is only valid in certain syntactic places. Patterns let x y tuple ranges 0 10 struct update syntax etc. but not as a tuple.
So obviously it got it wrong. Actually, I'm not really sure because I haven't tried to. I'm gonna open the temporary project. Just see if it compiles. Yeah, so ChatGPT is wrong on this one.
This is a fun Rust puzzle. Let's go step by step. Rust mainlet x y0 1 print b 066 yx first. Does this compile? No, this does not compile because rust 0 1 on the right hand side is an expression, not a pattern. The token rust is only valid in certain syntactic places. Patterns let x y tuple ranges 0 10 struct update syntax etc. but not as a tuple value element. So rust 0 1 is invalid rust syntax as a tuple expression. Why it looks confusing because on the left rust let x y means ignore all remaining earlier tuple fields, bind last 2 into x. Why that is valid pattern syntax. But on the right rust 0 1 rust expects actual values, not a rest pattern. If you intended a real tuple, maybe you meant rust let x y0 1 2 3 then x2 y3 because last 2 elements are captured. Then what about rust print b 066 yx? Let's inspect b 066. This is a byte string literal. Rust b 066 type rust static u8 3 contents rust 48 54 54 because ASCII 0 48 feet 6 inches 54 first index rust b 066 y returns a single u8. Example if y1 rust 54 then second index rust b 066 yx tries to index into a u8, but u8 is not indexable, so this also fails. Therefore full answer your exact code fails for 2 separate reasons. Error 1 rust 0 1 invalid tuple expression. Error 2 rust b 066 yx second indexing on u8. About this pattern specifically rust let x y tuple. This is valid if the RHS is a tuple with at least 2 elements. It means take the last 2 tuple fields. Examples rust let x y5 6 rightward arrow x5 y6 rust let x y1 2 3 4 rightward arrow x3 y4. Your question: if either side had more elements than the other, would it compile? Left side more than right side. Example rust let x, y, z1, 2 yes, x1, y2 wait no needs 3 explicit bindings. RHS has only 2 fields. So this fails. Need at least as many explicitly named positions as required. Rule pattern, Rust, A, B, C requires tuple length equals 3 because. Can match 0 or more earlier fields. Examples valid Rust let, A, B1, 2. Matches 0 fields. Valid Rust let, A, B9, 8, 7, 6. Matches first 2 fields. Invalid Rust let, A, B, C1, 2 need 3 fields. Only have 2. Can RHS have more elements? Yes. Rust let, x, y1, 2, 3, 4, 5 then, x4, y5, y Rust allows this because tuples have fixed known size at compile time. Compiler knows tuple ID exactly. So it rewrites, Rust let, x, y1, 2, 3, 4 is roughly, Rust x tuple point 2, y tuple point 3 no runtime search. Important restriction tuple. Can appear only once in pattern. Valid, Rust A, Z, X, Y, X, Y. Invalid, Rust, X. Ambiguous. If you wanted a working puzzle similar to yours, Rust main let, X, Y 0, 1, 1, 0 print. B, 066, X ASCII prints. 6 final summary your exact code does not compile because. Cannot be used as tuple value on RHS. B, 066, YX tries indexing a U8. But this part, Rust let, X, Y tuple is valid tuple destruct tiering. It means, bind the last 2 elements, ignore earlier ones. And yes, RHS may have more elements than explicitly listed because. Absorbs extras. One line intuition Rust, X, Y means, I only care about the tail of this tuple. If you like, I can also explain why Rust allows. For tuples but not arrays in the same way historically, and how tuple rest patterns are compiled internally.
Hmm. If it does compile, I think it makes sense to be 1. Because this unsigned integer and this would be true. But obviously I'm not really sure. I'm not sure if you can dereference the type. I don't understand the expression here very much. Actually, this one. Or X as a dereference as. Because you dereference the type and gets the value. Like, intuitively I think it kind of makes sense, but I'm not really sure about the compiler. So I'm just gonna guess this one. So it's a 0 size type and they have the same address. Just testing to see if the addresses are the same. Which wasn't what I was thinking initially. Yeah, I think it's because there's 2 levels here of indirection. So one of them is the array and the other one is the address. So it's an address to an array. And then this dereferences the address, which means that you get the address of the value inside the array. So check to see if the index of them, not the index, is the same thing that I was talking about with ChatGPT there just now. That even though there's 2 values here, because they're 0 size types, they don't take memory, they don't take space on memory. So they are at the same address, even though it's 2 different elements. I think that's what it's testing. The next one. When we pass the compiler, if it passes, write the expected output. I'm pretty sure this one I remember is because of this type here is not allowed as a return type. But if it was allowed, then I think it would return just the 0 size type here. Yeah. The return type, one of the proper return type of this function because it only panics some of the time, not all of the time. And this one I think I did on some of the string. I think it's gonna be option A. Function level. Primary, then the definition of add could not combine structure of. In structure 2 RHS. Hmm. Just for a function level type parameter. Yeah, so it's basically saying that you couldn't make it equal IHS equal to anything if it was a function parameter. And I think this is correct, but obviously, I think I'm going more from memory here. But I think that this is probably correct. So the last one is probably when you put function parameters or function types. When you put generic types on functions, then you can assume you can't constrain, but I'm pretty sure you can. From one of those examples that I was reviewing of the data structures, I think there was an error like that, where I did put. From what I vaguely remember, I think you can actually put the make it equal to something. I'm not really sure about this. Whatever, I'm just gonna go to the next one. This one I remember as well. I think it's an error because it doesn't matter that B is always false. It's still gonna evaluate what is inside. But I don't remember the nuances of this. So obviously, you're trying to print here. If this was never evaluated, then I think it would work because it wouldn't assign S to anything, which means that you would still have the string. But because this evaluates inside here, it's kind of like moving the ownership to S2, which means you can't use here. Well, it doesn't try to determine whether if statements will or won't execute. I guess it's just a default they chose for safety. It's easier and more secure to assume that it's always gonna run than to try to guess what times it's not gonna run. Whether the program will pass compiler. So X is a mutable pointer to the value. Y is a mutable pointer to the first value. Now this one is tough. Not really sure. If it does compile, then I think that this would be a pointer. It's a mutable pointer to the first value. Because here it gets the... I'm not sure actually. Maybe it is a mutable... It has to be a pointer because this would be an array. I think that it is a mutable pointer. When it does this, it should go to the next value. So this one will become 1. And then obviously this one dereferences the pointer, which gets the value and then increases, which becomes 2. But then this would have to be true as well, because then x would be pointing to the same value. Actually, yeah. Point 0 would still be 0, so it would be 0, 2 here, I think. I have no idea though. I'm just gonna guess this. Yeah, so it was what I was thinking. This one is very complicated. I went through this a couple of times, and I don't remember like really well. I think it has something to do with the order of precedence and the way that Rust is gonna evaluate the square brackets or this. Not square brackets. It's curly braces and this other one, the parentheses. I think there's 2 of them that are gonna print the ones here, and the other ones are gonna print 2. But I don't remember at all how it works. So this is a closure, which is basically kind of like a lambda function in other languages. When it calls x here, it's gonna have this whatever this function returns. So I think that this is what it's testing. It's testing to see if this will return the other function here, or would just return a 0 size type, I think. Yeah, 0 size type. And I think that for this one, he's gonna print 1 here. I'm gonna guess 1, and then for this one also 1. That should be 1. I do remember there's some of them that are 2 though. This is actually tough, because this is a loop as well, not a function. I guess it would be the same thing. The second one would just evaluate. It's calling the after actually here. I actually have no idea. I'm just gonna guess wrong because I don't remember. I think like the first shoe is something like this. I'm just gonna yes. Yeah, so it's the other way around. I remember the pattern but not the explanation. Still, this is kind of the reason why I don't remember really well, because the explanation is kind of confusing. Not just it's not that the explanation is confusing. I think it's just the original code is confusing. So the first two evaluate as the zero size type, and the other ones are functions that are called ones. Which possible friends? So here X is a closure that returns a zero size type. Yeah, I think that makes. So initially I thought that was gonna return the lambda. So I guess it just returns it doesn't evaluate this thing. So this one prints true. Hmm. Also, the never type is the exclamation mark. And looks like the return. Yeah, but then it is saying that the return on Rust is like this never type here. Is the primitive never type. So based on the other exercise, I think there is slightly different. Because it's said the other side said that the other quiz said that when you have that type, the never type is not gonna allow you to compile the function. Because sometimes it can panic and sometimes it doesn't. But maybe if you put a return there, it would crash as well. Oh, it's a logical war. So it becomes this type and then it becomes an OR instead of a closure. Hmm. And both of them are booleans. So this also, but this is slightly different, but also the same thing. This one, it breaks out of the loop instead of doing this fuckery here. Access software. Yeah, so this one is the most, is more intuitive than the other ones, just returns the lambda. Or the closure. Yeah, so this is also more intuitive. This returns a lambda and then there's gonna be 1. So this one is asking whether or not it's the same situation as the first one, where I had the parenthesis here. In this case, it prints 1 because it returns returns the size or zero size type, because it becomes an OR operation, because this returns that exclamation mark, and then both of them are bool, which is the same as implement this function, which panics, I think, without evaluating any value. So this becomes a zero size type in the end. So it's the 1. So this one evaluates to this instead. But when you don't have the parentheses, it just evaluates to the. I think it kind of makes sense. Yeah, it is more intuitive to be that way for sure. So just the most intuitive answer. So what is the other one that is 1? This one is 1. Is one of the tricky ones. What is the other one? Okay, so now it parses incorrectly. The printed value is 1. This is the other tricky one. Whenever you have this, it's gonna incorrectly parse to this. Was unintentionally broken, so it's not incorrect. Not incorrect, but they changed the behavior unintentionally. But I think it makes sense. So this one is one of the special cases, and this one. Also, I think that the first two are true because there's the. I don't understand because it's saying that since it changed, since the behavior changed. Oh, so before you used to print 2, this one, and now it prints 1. Yeah, so I think that the quiz is asking from the previous version. Actually, maybe not. No, it was talking about this one. So on this one, it used to print the same as this one. But now it just thinks that it is returning a lambda. So the behavior of this one is more similar to the behavior of this one. It's basically the same thing. Or this two here. They actually return the closure, and then the closure gets called, which means that you're gonna get 1. And then this one and this one, they are the exclamation mark, and then it does the OR operator, and it ends up returning the 0 size. So I think that's the. Yeah. Hopefully next time I remember this. I'm gonna stop streaming here. Next time I'm either gonna continue to review these structures or review the data structures and do the quizzes, or I'm going to try to convert micrograd into Rust. So see you then.